All right, so question number 9 says, this figure here shows the lines of electric potential, 100, 200, 300, 400 volts. Find the work that is required for a charge of 5 coulombs to be moved from 100 to 200 along path 1. So if we look at this, I'm just going to draw these for us to see. And so for part A, what we have to think about is, even though the lines are curved that way, we have to think that there's some positive charge over here. Because remember that the closer we get to a positive charge, the higher the electric potential. So we're going to have an object which has a charge of 5 coulombs, and it's going to move in this direction along path 1. So if we think about this, this is not what this positive charge object wants to do. It's naturally repelled by this positive charge object here, and so we have to do work in order to do that. So part A says find the work that is required if that charge is moved from 100 to 200. So remember, we can use the equation electric potential difference equals work over charge. So from that, we can say that the work then is equal to the potential difference times Q, and that's going to equal, and this is always final, so it's 200 minus 100 times Q, which is 5. So the work done is going to be 500 joules. That's how much work is required to move it from here to here. Part B then says how much work would be required if the same charge were moved along path number 2. And if we look at path number 2, that's moving from 100 to 300. So we're going to have our 300 volts here. And so path 2 is going to be in this here. So to solve for that, we're going to do the same process where our electric potential equals work over Q. Now what we should think about is, well, this whole time it's being repelled. And so if I'm moving it even closer, the repelling force is going to get even stronger as I get closer to this positively charged object. So I should have to do more work. It's going to be harder for me to move it from here to here than it is from here to here. It's just like lifting an object up. The higher I lift it, or the closer, the greater potential energy that I give it, the more work that's required. So for this one then, again, it's going to convert to work equals electric potential difference times Q, which is going to equal 300 minus 100, which is simply going to be 200, times my charge, which is 5. So my work required here is going to be 1,000 joules. Part C then says we're going to move to 300 along path 2, and then we're going to move back to 200 volts along path 3. And how much work is required? So if we look at that, it's going to be kind of combining everything that we just did. Okay, so for C, we're going to move this way and then back to here. So we're going to call this part 1 and then part 2 of C. So for part 1, our work is going to be electric potential times charge, which is going to be 200 volts, just like we did down here, right? Just like we did down here. It's 300, final is 300 minus 100 times 5. So that's 200 times 5, which that work is going to be 1,000 joules. For part 2 then, we're going to do the same thing. And this time though, it's going to be 200 volts, my final, minus my initial, which is 300, times my charge, which is 5. So now that's going to be a negative 100 times 5, which would mean that would be negative 500 joules. And so the total work required is simply going to be 500 joules. Why does that make sense? Well, if we think about this, would we have to physically do any work to actually bring this positively charged object here? No, absolutely not. It's actually going to be repelled naturally from this object. And so it's asking for the total work required to move it here. It's simply going to be 500 joules because we have a positive 1,000 joules to move it to here, and then negative 500 joules to move it there. So the total work is 500. Okay, and this really gets to the point of electric potential and why we can use this and why we don't really worry about distance and time is because it's simply based on initial position and final position. So in path 1, our initial and final positions are the same as path 3, or excuse me, as this path here and then back there. So the total work done is going to be the same.